So today we'll discuss about Ptolemy's theorem. So statement is that the rectangle contained by the diagonals of a cyclic quadrilateral is equal to the sum of the rectangles contained by pairs of its opposite sides. So what do you mean by rectangle contained by any two sides? So basically rectangle contained by any two sides with lengths A and B equals AB. So when we say that the rectangle contained by the diagonals of a cyclic quadrilateral, then we mean the product of the lengths of two diagonals, that is in this case AC into BD. Is equal to the sum of the rectangles contained by pairs of its opposite sides. So first pair is AB, CD. So rectangle contained by them will be AB into CD. And second pair we have got AD and BC. So second pair we have AD and BC. So sum of the rectangle contained by diagonals and the sum of rectangle contained by the diagonals and the rectangle contained by two pairs of opposite sides is and sum of these two will be equal to this. So basically we have to prove this. AC into BD equals AB into CD plus AD into BC. So to prove it, first of all I will draw AE with E being on diagonal BD such that angle CAD equals angle BAE. I have assumed that BAC angle is greater than angle CAD. So whichever side you assume, the answer will not be different. So angle BAE, let's say it's X, then angle CAD, it's also X. So angle BAE equals angle CAD. This is clear. This is via construction. Now this AD is a chord, and so it will subtend equal angles at point B and point C because both these points lie on the circle and in the same segment. So if this is Y, then this is Y too. So we've got angle ABD equals angle ACD. Angles subtended by same chord. So now if we consider these two triangles, triangle ABE and triangle ACD, then clearly these two are similar via AA similarity criteria. So we have got triangle ABE similar to triangle ACD. Now this implies AB by AC equals B by CD. So we have come to this result that AB by AC equals B by CD. Now this implies AB into CD equals AC into B. Let's name it as equation number 1. Now angle BAC. Now angle BAC equals angle BAE, that is X, plus angle EAC, angle BAE plus angle EAC. Angle BAE is equal to angle CAD. This is because we have constructed angle BAE such that angle BAE equals angle CAD. So this becomes angle CAD plus angle EAC, which is actually angle EAD. Now this AB is a chord, and it is so it must so the angles obtained by this chord AB at point C and point D, that is angle ACB and angle ADB, should be equal because both these points lie on the circle and within the same segment. So if this is Z, then this is Z too. So we have angle ACB equals angle ADB. Now if you consider these two triangles, in triangle ABC and triangle AED, then in triangle ABC and triangle AED, angle BAC equals angle DAE, angle BAC equals angle EAD. From here, and angle ACB equals angle ADE. If you name it as 2 and this is 3, then this is from 2 and this is from 3. So we have triangle ABC is similar to triangle AED via AA similarity criterion. So we just saw triangle ABC was similar to triangle AED. This implies BC by D equals AC by AD. Now this means BC into AD equals AC into D. Now I'm naming it as 4. Now if we add 1 and 4, we have AB into CD plus BC into AD equals AC into B plus AC into D. This is taking AC common, we get AC into B plus D, and BE plus DE is actually BD. So this becomes AC into BD. So this is the final result, and hence our Ptolemy's theorem is proved. So now we will discuss one corollary related to this Ptolemy's theorem. So first of all, I should tell you what is a corollary. A corollary is actually a statement or a proof that uses a theorem as its base. So basically, one could say like corollary is derived from a particular theorem. So this corollary states that if a point be taken anywhere on the circumcircle of an equilateral triangle, its distance from one of the vertices is equal to the sum of its distances from the remaining vertices. For example, I have taken an equilateral triangle ABC, and this is the circumcircle of this equilateral triangle. So to prove it, let's take a point P. Let's say we take P here and join it to the two of the vertices, B and C in this case. Now ABPC is a cyclic quadrilateral. So if we apply Ptolemy's theorem here, then we will be getting product of diagonals, that is AP into BC, equals sum of products of opposite pairs of opposite sides, that is AB into CB plus AC into BB. So this is the cyclic quadrilateral. This AP is diagonal, BC is diagonal, so AP into BC equals AC into BB plus AB into CB. Now since this is an equilateral triangle, so AB, AC and BC are equal. So if I replace here BC by AB and AC by AB, then we'll arrive to this result: AB equals CP plus BP. Now AB equals CP plus BP. What does this mean? This means that its distance from vertex A, the distance of point P from vertex A, that is AB, is equal to its distance equal to the sum of its distance from vertex B, that is BB, and its distance from vertex C, that is CP. So AP equals BB plus CP, and hence our result is true. If you take this point somewhere on this arc AC, then you will be getting BP equals AP plus CP. If you take this point on this arc, then you will be getting PC equals AP plus BP. So our result, distance of point P from one of the vertices is equal to the sum of distances from the remaining vertices, is proved.